Good morning, Applied Physics A students. This is Mrs. Krumschreider, and these are some notes for you for Chapter 3, Sections 5 and 6. We're continuing to talk about mass, weight, and inertia. So, Section 3.5 was titled Mass, a Measure of Inertia. And we're going to start by focusing, obviously, on mass. And hopefully you've learned about mass in the past, but mass is roughly the amount of material present in an object. Sort of the science definition of mass is that mass is the amount of matter in an object. And as we're talking about inertia as well, we can also say that mass is a measure of the inertia of an object. So what that sort of means is that the more mass an object has, the greater its inertia. And the more force it takes to change its state of motion. And your book sort of explained this with this idea of like a can of a vegetable can. So say a can of green beans, okay? If you kick that can or throw that can and it has the green beans in it and it weighs about a pound, okay, that has a different mass, okay, and requires more inertia to get it to throw it than it does if that can is empty. Like you've taken the green beans out of it and now it's empty, okay? Right? It's much easier to throw that can when it's empty because it has less mass, therefore it has less inertia, and it takes less force to change the can's state of motion. Mass is usually measured in grams or kilograms or kilograms. Okay, so again, mass is the amount of matter in an object. It is also a measure of the inertia of an object. So the more matter an object has, the more mass it has, the more inertia it has. The less matter an object contains, the less mass it has, the less inertia it has. One of the things that you need to understand is that mass is not volume. They are not the same things. Okay. So what then is volume? You have probably learned about volume in a math class in the past. Volume is a measure of space. Specifically in science, we typically define volume as the amount of space that matter occupies. Volume in science class is usually measured in cubic centimeters, cubic meters, and liters. Keep in mind that a large mass doesn't always mean a large volume. An example of this is if I have a shoebox full of cotton balls versus that same shoebox full of nails. Right? These both, okay, they have equal volumes because they are the same shoebox, but they have different masses. Right? The cotton balls will have much less mass, which means they contain much less matter than the nails do. Another example of this is to look at or think about a pillow versus a car battery. Right, most of you have probably seen a car battery somewhere. Okay, so this pillow, right? The pillow has, especially if it's like a king size pillow from your bed, it has a large volume, but a relatively small mass, which also would mean it would have small inertia. Whereas a car battery has a pretty small volume compared to the pillow, but a large mass, which would mean it also has a large inertia. Okay, so mass and volume, sometimes something that is very massive also has a very large volume. For example, a semi-truck, okay? But sometimes things that are pretty massive have a pretty small volume. Another point that your book wants to make sure that you understand, and that is very important to understanding physics, is that mass is not weight. Okay. Mass, again, our definition, our science definition of mass is the amount of matter in an object. Mass is considered a fundamental science concept, okay, and is more fundamental than weight is. And the reason that it's considered more fundamental is because mass depends on the number and kinds of atoms that make it up. And basically all that's saying is that, for example, you as a person are made up of different kinds of atoms than paper is. Okay, so that's all that is saying, is that different kinds of substances or different objects that you see around you, they're made up of different kinds of atoms and different numbers of atoms. Okay. And an important concept about mass is that mass is the same everywhere. It does not change with location, because as we start to talk about weight here in just a moment, we're going to see that weight does change with location. So what then is weight? Again, our science definition of weight is that weight is actually the force of gravity on an object. What that means is that weight depends on the force of gravity and the mass of the object. So what that means is, and I don't know if you knew this or not, but your weight would not actually be the same everywhere on planet Earth, because the gravity here on Earth isn't always the same. The gravitational pull on you is different when you're at the top of a really high mountain than it is when you're at sea level, which means your weight would actually change a little bit. Okay, so weight depends upon the force of gravity and the mass of an object. Now, your mass doesn't change depending upon where you are on Earth, but the force of gravity does. So, an important kind of thing to understand about weight is that weight is really measuring the gravitational attraction to Earth. It changes with location. So remember mass, right? That was our last comment about mass, was that mass does not change with location, okay? But weight changes with location. For example, the weight of a car battery, because we talked about a battery just a little bit ago, on Earth is different than the weight of the car battery on the moon. In fact, because the moon's gravitational pull is about 1/6 the weight, or the gravitational pull on Earth, the weight of the car battery on the moon would be 1/6 its weight here on Earth. But, and again, remember, the mass of that car battery is the same on Earth and the moon. So mass does not change, but weight does. Again, for the most part in your textbook, we're going to say that mass is inertia. So inertia, or mass, depends only on the matter in an object, not its location. And again, that's because it's the same as mass. And because mass does not change with location, then inertia does not change with location. Again, remember our definition of mass. Obviously, this definition is pretty important, right? Because, again, this is about the third time we've done this definition. Mass is the quantity, which is kind of a fancy word for amount, of matter in an object. Mass is a measure of the inertia which your textbook kind of tends to call laziness, right? That resistance to a change. Whether it's resistance like the object's at rest, it doesn't want to not be at rest, or if the object's in motion, it doesn't want to stop being in motion, okay? So it's a measure of the inertia or laziness that an object exhibits or shows in response to any effort made to start it, stop it, or otherwise change its motion. Right? So again, to start it means the object's at rest and you want to get it started. Okay? The more mass an object has, the more inertia required to get it started. To stop it, so the object's already moving and you want to stop it, if the object is more massive, it's going to take more inertia to stop it. Okay, so that's what we're saying there. Again, as we already mentioned, mass and weight are not the same thing. Weight is the force of gravity on an object. However, mass and weight are proportional to each other. So what proportional means is that the more mass an object has, that means it has more weight, which this wasn't true. Okay? And the less mass means less weight. So we want to take a look at the page 37 think question. There actually are a couple questions there. The first question says, does a 2-kilogram bunch of bananas have twice as much inertia as a 1-kilogram loaf of bread? Yes, it does. Because, this is my abbreviation for because, twice the mass means twice the inertia. They're directly proportional. As you have more mass, you have more inertia. The second part is twice as much mass. So it's saying, does a 2-kilogram bunch of bananas have twice as much mass as a 1-kilogram loaf of bread? Again, the answer is yes. Because 2 times the mass is always 2 times the mass, right? 1 kilogram versus 2 kilograms, that's twice as much. The third question, does a 2 kilogram bunch of bananas have twice as much volume as a 1 kilogram loaf of bread? No, because volume, remember, is a measure of amount of space. Generally, I'd say even a pretty good sized bunch of bananas really has a very different volume than a loaf of bread would. And the last question, does a 2 kilogram bunch of bananas have twice as much weight when weighed in the same location as a 1 kilogram loaf of bread? The answer to that one is yes, because again, 2 times the mass means 2 times the weight. Now, why did they mention in the same location? Because they wanted you to recognize that the gravitational pull, okay, was the same. All right. 1 kilogram or kilogram weighs 10 newtons. So remember when we looked in chapter 2 at forces, we measured our forces in newtons. So we're going to talk about how does a newton relate to a kilogram. So keep in mind here in the United States, we're a little bit backwards in that, we use units that pretty much no one else in the world does. So we measure the amount of matter by its gravitational pull to Earth. Basically by weight. Because the unit we use, a pound. And pound is measuring gravitational pull or weight. Again, we're sort of the weirdos in the world, okay? Because pretty much everywhere else in the world, matter is measured in a kilogram. And because we're in science class, this is also what's used in science. So when we talk about matter, we're typically going to talk about it in grams or kilograms. So kilogram is the unit we use, and it is abbreviated a lowercase k. So I actually use a cursive lowercase k because it looks different than a capital K, okay? You can use a lowercase k, just make sure it's clearly lowercase, and then G. 1 kilogram is equal to 2.2 pounds. Which means your weight would be more kilograms than what it currently is if you measured it in kilograms. So I think I'll stick with pounds. And the SI unit of mass is the kilogram. SI stands for Le Système International de Unité. It's an international system of units that's used around the world by scientists. Remember, or know that it's used so that everybody's communicating the same way. Every scientist around the world would know exactly how much a kilogram is. A newton, then, named after Sir Isaac Newton, is the SI unit of force. And you'll remember back in chapter 2, we used newtons. Again, the SI symbol is a capital N. 1 kilogram equals 10 newtons. So if I want to take the number of kilograms and figure out what its weight is in newtons, I'd multiply it by 10 to get my weight in newtons. And if I have my force in newtons, I would divide it by 10 to get my mass in kilograms. So to kind of do a quick example of those, okay, if I have 15 kilograms times 10 would be 150 newtons. If I have 20 newtons, and I want to know the mass in kilograms, I would divide it by 10 and get 2 kilograms. Okay, so that's how you can change between those units. All right. The last section kind of goes back to Copernicus's idea about the moving Earth. And there's kind of an example here, and to be very honest, they explain it better than I can, so I just want to kind of read it to get you thinking, okay? Copernicus announced the idea of a moving Earth in the 16th century. The controversial idea stimulated much argument and debate. One of the arguments against a moving Earth was as follows. Consider a bird sitting at rest in the top of a tall tree. On the ground below is a fat, juicy worm. The bird sees the worm, drops down vertically, and catches it. It was argued that this would not be possible if Earth moved as Copernicus suggested. If Copernicus were correct, Earth would have to travel at a speed of 107,000 kilometers per hour to circle the sun in 1 year. Convert this speed to kilometers per second and you'll get 30 kilometers per second. Even if the bird could descend from its branch in 1 second, the worm would have been swept away by the moving Earth for a distance of 30 kilometers. For the bird to catch the worm under this circumstance would be an impossible task. The fact that birds do catch worms from high tree branches seemed to be clear evidence that Earth must be at rest. Okay, so that was kind of part of the challenge. Now, again, you've learned since you were little, right, that the Earth is moving. But that was sort of a new idea. It was a new idea. It wasn't sort of a new idea. Okay, and they were kind of struggling with it, and that was sort of their problem. And so the way to explain the bird catching that worm is this idea that the objects move with Earth. Because the law of inertia, which is Newton's first law, states that objects in motion remain in motion if no unbalanced forces act on them. So that example with the bird and the tree and the worm on the ground. Oops. The idea here is that that bird is able to drop straight down to get the worm because the bird, the tree, the worm, the ground, or the earth are all moving 30 kilometers per second. They're all moving together. Okay? So the bird is able to drop straight down to get that worm. because the bird, the tree it's sitting in, the worm, the ground or the earth are all moving 30 kilometers per second. This is also true, and you see this when you think about objects in a vehicle. For example, if you flip a coin in an airplane, you're able to catch it because the coin, the person, and the airplane are all moving at the same speed. So, a thought question, kind of to challenge you now, if you understand this. If you can answer this question, then you understand this pretty well. At the circus, when the horseback rider standing in his saddle approaches a hoop, does he jump forward, backward, or straight up? From the saddle? And we'll also kind of answer what physics law is demonstrated here. So think about that for a moment and see if you can come up with an answer on your own, right? So maybe you've seen this before, right? We have a horseback, a person on a horse, and they're standing up in the saddle and they're coming up to a hoop, okay, that's at the height of the person. So to continue, the person has to do something. They can't stay standing on the horse. They're going to have to jump. So the question is, does this person standing on the horse, do they jump forward through that hoop? Do they jump backward through that hoop? Or do they jump straight up from the saddle to go through that hoop? Hopefully you said straight up. Why? Because the horse and the rider are both in motion, right? They have inertia. And an object in motion is going to stay in motion. So although that rider jumps straight up, they were already traveling forward at the same speed as the horse. And when they jump up, they're going to continue to travel forward at the same speed as the horse. And when they come back down, they should land on the horse. What law is this? This is Newton's first law, known as the law of inertia. All right, that brings us to the end of chapter 3. Have a great day, and I will talk to you tomorrow.